Alrighty, in this video, we're going to look and discuss at physical properties and changes, chemical properties and changes, as well as other types of properties that chemists can use to identify different pieces of whether it be an experiment or qualitative observations. So, physical properties and changes. One thing about properties allow us to distinguish one substance from another. So, if you have a physical property, for example, that's a characteristic not associated with the change in chemical composition. So, I know the definition seems kind of wonky, but basically, what a physical property is, if I were to have a substance and if I were to use, let's say, my five senses plus some techniques that I can use in a lab, maybe adding some heat or removing some heat or different things like that, or maybe do some measurements, I can identify them. So, a couple of examples of physical properties. Density is a physical property. I can measure density without doing a chemical reaction, right? I can put, whatever I might have. Maybe I want to weigh it and then find the volume of it to find the density. Or maybe I want to do the water displacement method. Solubility, how well something dissolves in water or other solvents. Odor, now I'm starting to use my senses. Does it stink? Does it have a smell? Color, you use your vision. Does it have a specific color to it? Again, these are all properties that you can do without doing a chemical reaction. I can look at my desk and tell you it's a black desk, right? That's what it is. I can look at my desk and tell you it doesn't have an odor, things like that. The hardness, is it easily broken? What's the melting point? If I heat something up to a certain point, when's it going to melt? Or if I take that liquid and heat it up enough, when's it going to boil? And then lastly, electrical conductivity. If I add some electricity to it, is it going to transfer that electricity to something else? So these are all physical properties. Now keep in mind, some physical properties are only observed during a physical change. So physical change basically changes the state of matter, but not the identity. So if we think about water, for example, if I have liquid water, and let's say I add a ton of heat to it, eventually I'm going to get those water molecules moving really quickly, and they're going to convert into gas molecules. This is a physical change. When I do this physical change, I can then measure the boiling point, right? Or if I take a solid and add a lot of heat to it, or maybe not a lot of heat, and I turn it into a liquid, for example, again, that's another physical property. I'm observing it through a physical change. We'll just stick with those for right now. So again, these are examples of physical properties and physical changes that you can see. Now, we can actually further classify physical changes, and we do need to know by definition what some of these things are. And it makes it just easier for us to discuss in a classroom and more specifically in a lab setting. It allows us to use better verbiage. If I take a solid, add some heat to it, and turn it into a liquid, that process is known as melting. Ice does this all the time. You leave it on the countertop, the heat from the air around it is going to transfer, it's going to turn it into a liquid. That's the process of melting. It has to be above 0 degrees Celsius for that to happen. If I take that same water and let's say I put it back in the freezer, and the freezer is below 0 degrees Celsius, slowly but surely, it's going to freeze. Liquid to solid is freezing. Liquid to a gas, the broad umbrella term to describe that change is known as vaporization. Now, more often than not, you'll hear it between one of two things. You'll hear boiling, which means the change is occurring throughout the entire liquid, so I can choose particles at the bottom of it, at the middle of it, at the top of it. That's all boiling. Evaporation only occurs at the surface, and this is where it's different. If I were to leave, for example, a bottle of water outside, and let's say I were to take the cap off, the water that's going to, from the sunlight that's transferring energy to that water, only the particles at the surface of that liquid are going to evaporate off. If I heat it up from the bottom, though, really add a ton of energy to the whole sample, it's going to boil throughout. So vaporization can happen two different ways, at the surface or throughout. The next one we have to know is gas to liquid. So that's condensation. That's essentially what happens when you take a cold soda or pop or whatever you call it. You take it out of the fridge, you set it at the countertop. That really cold can that is on that aluminum is going to basically condense the air and whatnot that's surrounding it, and it's going to turn to a liquid. It's going to condensate on the side of that can. That's condensation. Now, these two are a little less common. Going from a solid directly to a gas, that's essentially what dry ice does. That's sublimation. Okay, and then going from a gas to a solid, that's essentially what frost is. So if you have frost that occurs on a windshield or something like that, that's deposition. So these two are less common, but we still gotta know. So going from a solid to a gas, sublimation. The reverse of that process, going from a gas to a solid, that's deposition. Now, one thing that we have to keep in mind is that when we go from a solid to a liquid to a gas, I have to put energy in to make that happen. So I have to apply heat or add energy to whatever sample I have to get that to happen. Now, keep in mind, depending on what the sample is, it might not be a lot of heat, but it's got to be some amount of heat to make that happen. The other thing that we want to think about is going from the reverse. So if I take a gas and turn it to a liquid, or if I take a liquid and turn it to a solid, I need to recognize that energy is going to be released from that system. So going from a gas to a liquid, for example, that's going to basically cool it down. The heat's going to be released. From going from liquid to a solid, it's going to cool it down. The energy has to go somewhere. It's going to be released. Whereas the reverse, you have to put heat in to make that happen. That's what those arrows represent there. All right, let's go into chemical properties. So, with regards to chemical properties and chemical changes, these always produce one or more types of matter that differ from the matter present before the change. So when we talk about a chemical change, that is a chemical reaction. So we can use chemical reactions to refer to chemical changes. They're essentially the same thing. They're just used interchangeably. So we want to make sure we understand that these mean the same thing. Now, when we have chemical changes, your atoms are simply rearranged to form different substances. So again, we want to keep in mind that it's not like we're just, randomly generating new stuff. We're generally just transferring the stuff around. Now, if a proton exchanges here or there, then yeah, maybe we have a new element that's being formed. But again, that's usually in nuclear chemistry, and we're not really going to delve into that in this course too deeply. So when we have a chemical change, that is when we can say, here are the chemical properties. We can observe chemical properties without doing a chemical reaction or without a chemical reaction happening. So the most common chemical changes you'll experience are usually a change in energy or a change in heat, for example. So maybe something will get hotter or something will get colder, or it'll feel that way to the touch. Or if you put a thermometer in, you'll see the reading drop or the reading increase. And the other one is a change in color. And again, specifically, these are changes. It's not just the presence of heat being there or the presence of cold being there. It's the fact that it was something and now it's something else. So maybe it was cool initially, but then it got really hot when I mixed those two chemicals together. Or it was hot initially, and then when I mixed those other chemicals in it, now it's cold. Same thing with the color. Maybe it was clear initially, and now it's white. That's a good example of a chemical change. Now, some of the properties we need to know with regards to chemical properties: flammability. Basically, how does it catch on? Does it catch on fire well? Does it not? Is it not going to react volatilely? Toxicity, acidity, and reactivity. Notice all these ends with those ITYs, right? Toxicity, acidity, reactivity, all this, flammability, etc. Now, when we talk about chemical and physical changes, different things are happening in that microscopic domain, like we saw with this particle diagrams in the last video. During a physical change, the forces that are basically between different substances are what's being changed. So if we have a solid, for example, let's say they're really, pardon the overlap there, that shouldn't be there, they should be really close but not overlapping. Maybe they look like this. So there are forces that are holding these things together. Okay, these little brackets are represented, they're touching each other, or they're very close, and they're being attached to each other. By adding some energy to it, and let's say I take that ice and I melt it, now these particles are a little more separated. So the force is actually holding multiples of these together. They're going to either split apart or come back together depending on the physical change. So we're not really modifying what it is. We're just modifying how close they are to each other or how attracted they are to each other. So during freezing, multiple water molecules are brought closer together and eventually form a lattice structure. We saw that in the particle diagrams. The hydrogens and oxygen are all still connected to one another to form H2O, aka you're not separating the different atoms that make up water. You're just separating multiple waters from one another. These are commonly known as intermolecular forces. Inter meaning between, like multiple things. So if you think of I-95, for example, Interstate 95, I-95 just doesn't run through Florida, right? It runs through Florida, Georgia, South Carolina, North Carolina, Virginia, Delaware, Maryland, all the way up the coast, right? Connecticut, New York, etc. So I-95 connects multiple states together, okay? So it's inter, just like interstate, connects a lot of them together. Now during chemical changes, the forces within substances are changed. So now when we take our little water molecule, we have our little red circle here, which typically represents oxygen, and we have two hydrogens connected to it. Now we're changing that, so now we have two hydrogens connected together, and we'll have two oxygens connected together. And again, that's not going to balance, so if you're kind of nitpicky like me, you'll draw it so it looks correctly. So now that looks good, and then I have to have one of those there as well. So this is a chemical change because we're actually cleaving, or we're separating the stuff that makes up a molecule. So if you pass electricity through liquid water, which is a process known as electrolysis, you're going to actually split or cleave that water into its one oxygen atom. Really, it's going to be two because you'll see it represented here. The oxygen atoms and the hydrogen atoms, respectively. So main difference between the changes are what's happening to the atoms of whatever that stuff is. And the last thing we have to recognize is that we have multiple different types of properties. When we look at physical properties, we can label them as intensive or we can label them as extensive. So if you think of extensive, think of the word extend, aka as I add more stuff or as I add more amount of matter, that property is going to extend. It's going to either grow or maybe it might shrink depending on what's going on here. So for example, if I take mass, let's say I have one pencil. Let's say I have one pencil, and that has a mass of 5 grams. If I have 2 pencils, that has a mass of 10 grams. And 3 pencils have the mass of 15 grams. Notice, as I add more pencils, the mass is increasing. That property is getting larger as I add more and more stuff. The same thing goes with volume, length, weight, and heat, right? If I add, more energy, it's going to get hotter, right? If I add more heat, the temperature is going to raise. Things like that. So intensive basically is saying that the property is independent of however much stuff is there. So essentially what that means is no matter how much stuff I have, the property isn't going to change. Let's talk about temperature, for example. Let's say I have a cup of water. It's a really bad cup, but whatever. Got some water in it. Let's say it's at 50 degrees Celsius. This temperature is indicating to me that this water is 50 degrees Celsius. Now let's say I have a drop of water. And let's say that drop of water is also 50 degrees Celsius. Is the temperature any different based on the amount of matter I have? No, it's not. I could have a swimming pool of water. I can have a droplet of water. No matter how much water I have, the temperature is the same. Same thing goes with density and boiling point and melting point. No matter how much water I have at 100 degrees Celsius, it's going to reach that amount. So something to keep in mind there. Okay, so no matter how much I have, it'll be 100 degrees Celsius. Now keep in mind, it might take more heat to increase that temperature, but it doesn't matter. Water's going to boil at 100 degrees Celsius. That's going to wrap up this video.